Let's see if I'm streaming. All right. I think this is working. Oh, hey, everything went green. I think we're back. Cool. Let's try this. I need to flip this around. Do this 2 over 2 here. So yeah, yesterday I tried streaming about partial fractions, and I went for an hour and a half, and then found out at the end that the stream wasn't on. And I don't know if I was a technical thing, if it like was on and then stopped being on or something, but there was no record of the stream existing. I think maybe I just never clicked go live. I've double checked, and I think I'm live now. And the connection's good. I got this green square here is supposed to be a good sign. I was having troubles this morning, but I think we're good. Let's do partial fractions. I asked for homework questions. I didn't get anyone asking me questions about the homework. I'm feeling anxious about this because, like, when I teach this live, I have a million students who ask questions, and now nobody's asking questions, and I don't know if that's because you can go back to the video easier than you can in a live class, or if nobody gets what's going on, or nobody's doing any homework. I don't know. If you're not doing any homework, you should go do some homework. If you have questions, you should ask me your questions. Let's talk about partial fractions. I had a teacher when I was an undergrad who said that there's an expression, nothing in life is certain but death and taxes. Well, in math, nothing is certain but death, taxes, and partial fractions. Partial fractions is this specific trick. We're going to learn it because it lets you integrate a few specific functions. But it's really useful in lots and lots of contexts. I said in the first day of class that if you look at your course catalog, probably there's a ton of math classes that say they need 142. A bunch of those say they need 142 just because they want you to have seen partial fractions before. Let's talk about what partial fractions does. If I have 1 over x minus 3 plus 6 over x plus 1, these are separate fractions, and we know how to add fractions. We need to get a common denominator. Our common denominator will be, we need x minus 3, x plus 1. The first one I add an x plus 1 to the top and bottom. The second one I put an x minus 3 on top and bottom. This becomes, now over a common denominator, I get x plus 1 from the first one plus 6x minus 18 from the second one. I end up with 7x minus 17 over x plus 1, x minus 3. Hooray, we know how to add fractions. Nobody's impressed. Why did I do this? The reason I did this is because maybe someday I'm going to ask you to integrate 7x minus 17 over x plus 1, x minus 3. And you can try a few things. If you FOIL out the bottom and complete the square, I think you can do a trig substitution and that works. I'm not sure how bad it is. I wouldn't really want to do it like that. The main thing I'd like to do is, in light of that adding fractions thing we just did on top, I know that 7x minus 17 can be rewritten as 1 over x minus 3 plus 6 over x plus 1. So I can do this integral by doing the integral of 1 over x minus 3 plus 6 over x plus 1. These are easy things to integrate. Integral of 1 over x minus 3 is natural log absolute value x minus 3. Integral of 6 over x plus 1 is 6 natural log absolute value x plus 1. These are the baby type substitution that we wanted to be comfortable doing when we did parts. So this integral is not only doable, but it's very easy if I can look at this fraction and identify that it's a sum of simpler, easier to integrate fractions. And that's what partial fractions is about. It's about taking one big fraction and decomposing it as the sum of smaller, simpler fractions. Sending a message to the class to let them know I'm not. Oh, I said love now. I meant to say live now. I am live now. Talking about partial fractions. So the goal of partial fractions is to look at something like this and figure out how to break it up into stuff like this. And here's how that works. The goal of partial fractions is to take a rational function. Have you heard the word rational function? A rational function is a polynomial over a polynomial. Should I talk about the word rational function for a second? A rational number is a number you can write as a fraction, like 2/3 or 5/6, and pi is not a rational number, because you can't write it as a ratio of two integers. In a lot of mathematical ways, the set of all polynomials is a lot like the set of all integers. It's called a ring. You can add polynomials, you can multiply polynomials, you can divide polynomials if you're okay with there being a remainder, but you can't always divide polynomials without remainder. Same deal with integers. If you allow yourself to write a fraction of polynomials, then you extend the ring to a field the same way that you can build the rational numbers out of the integers, and now you can divide them. You can divide two fractions and you'll always get a fraction. You can multiply, divide, add, subtract rational functions and get another rational function. Anyway, our goal is to take a rational function and express it as a sum of simpler rational functions. What do we mean by simpler? In particular, we want the bottom to be an indivisible, a small if the bottom factors, you want to break it up into things where the bottom doesn't factor, or at least the bottom is a power of something that doesn't factor. I'll show you what this means. Let's talk about step 0. Step 0 is the degree of the top should be smaller than the degree of the bottom. And if it's not, do long division so that it is. Ugh. Yeah, you need to remember how to do long division of polynomials. If you haven't done this in a while, find yourself a bunch of examples and do it. If you haven't done it in a while, I think it's useful to go 1, 3, 4, 9, 1 and divide that by, I don't know, 12. This is do some long division with numbers. I think this is really helpful. It's really, I used to do a lot of math tutoring, and it's fun to get someone to do a long division with numbers because, like, this got burned into your brain really hard in 3rd or 4th grade whenever you learned long division. You write this down and your hands will start doing the process of long division, and it wakes up the gears in your brain. And once you remember how to do this, it's not so bad to do it for polynomials. So yeah, I had x squared minus 4x minus 3 over x squared plus 1. This is the deal where every term of the polynomial is like a digit. I will do this one example. This one example is probably not enough to know everything to do for long division of fractions. If you somehow got through a pre-calc class without seeing how to do this, you probably need to go Google how to do this. This is a thing you need for right now. You look at first digit divided by first digit. What's x squared divided by x squared? It's 1. 1 is a constant. I put it on the constant column. I multiply 1 times x squared plus 0x plus 1. I subtract negative 4 minus 0 is negative 4. Negative 3 minus 1 is negative 4. My new thing here is degree smaller than x squared, so I can't do the next step. My next step would be what's 4x over x squared. That you don't get a polynomial when you divide first digit by first digit. So that's it, you're done. This fraction turns out to equal quotient plus remainder over denominator. So if I was trying to integrate this, I might do the long division and find that it equals this. This is something I can integrate. This is also hopefully something I can integrate. This is the first step of partial fractions, is we need the top to be smaller than the bottom. If it isn't, then long division will give us a polynomial, which we know how to integrate, and the remainder will be smaller than the bottom, so you get it so that step 0 is satisfied. Most of the time you don't have to do this, but at the beginning of every partial fractions problem, you should double check that whether you need to do this. Step 1, you need to factor the denominator. And you need to group common factors. Factoring is one of those things that is it's a hard problem in general. If you hand someone a 7th degree polynomial, there's a good chance they just don't know how to factor it. There are tricks that you will learn in later classes, or I don't know what classes you're taking, but there are tricks you can learn that let you factor polynomials at least to the point that we need them to be done here. Some books will say factor it into linear and quadratics. You don't actually need to do this. The thing you do need to do, though, is at least factor it into so that none of the two factors on bottom have a common root. So for example, if I had 1 over x minus 2 and I had x squared minus 5x plus 6, this thing is factorable. What does it factor into? What is it? Multiply to get 6, add to get negative 5. They'll both be negative. X minus 2, x minus 3. Hey, this x minus 2 and this x minus 2 need to get grouped together is the main thing. This wasn't factored enough because the root of x minus 2 is shared among the group. And the fact that I have a common root of x minus 2 needs to become visible. That's an x minus 2 squared, x minus 3. We need to find the fact that there's a repeated factor here. If I had 1 over x squared, x minus 2, x squared minus 11x plus 30, 2 is not a root of this. The fact that they don't interact, that's fine. This thing I can do, I don't need to factor this all the way. I do need to factor this all the way because this root of x minus 2, we need to discover that x minus 2 is a thing that shows up as a repeated root. I'm going to do one where we mess that up in a second on purpose, so you see what that looks like, so that you know when you find that mistake, this is the cause of it. In the abstract, you can always factor a polynomial into linears and quadratics. You might not be able to do that in practice, and it's good to sort of acknowledge that partial fractions is doable. Like, I've seen books that say you have to get into linears and quadratics, and the fact is you don't have to do that. If the abstract capability of doing that doesn't translate into I can actually get that done, being able to split it up the amount that you can split it up is useful. There's also weird versions of this. If you have a factor of x minus 3 and a factor of 3 minus x and maybe some other factors, you need to be able to recognize that, hey, these two things are the same, but they're off by a minus sign. You need to factor the minus 1 out of this and get that x minus 3 times negative 1 x minus 3. You can pull the negative 1 to the top and write that as x minus 3 squared, x squared plus 1. You need to be able to recognize that these two things are secretly the same factor and group them together after factoring out the minus 1. Maybe you factor out other constants. Again, the same rule that's going on is these two polynomials both have a common root of 3, so they need to get grouped. Or you need to factor them until there is a common factor that you can group. Maybe there's something, maybe this is a gross polynomial that has 3 as a root, and this is a gross polynomial that has 3 as a root. If they both have 3 as a root, factor out that x minus 3 from both and smush them together is the thing you need to do. So factor the denominator, group common factors. Step 2, you never need to factor the top, by the way, so that's nice. Step 2 is state the form of the decomposition. And what we're getting at here is every factor of the denominator contributes a term or terms to the form. If I have stuff on top and the first factor is an x minus 2 times other stuff, then I'm expecting x minus 2 to be a denominator when I split it up. I'm expecting to get something over x minus 2. Okay? If I have an x minus 2 squared, then not only do I expect to get something over x minus 2, I'm also going to get a term over x minus 2 squared. So if I had x squared minus 3 over, let's say, x minus 1, x plus 4, x minus 6, the form of the decomposition is it's going to be something over x minus 1, something over x plus 4, something over x minus 6. Our goal then would be find the a, b, and c that make this equation true. And we'll talk about how to do that, but I want to get to the more complicated versions of what is the form. If you have something over, if there's repetition of your factors, then like we said, you need to keep repeating terms, counting up the power until you've reached the power you want. This is going to be something over x minus 1, something over x minus 1 squared, done with the x minus 1 squared. There's going to be something over x plus 4, something over x plus 4 squared, something over x plus 4 cubed. Now we're done with those. And then something over x minus 6. This is what we're hoping to split this thing up into. Right? Okay. So far, everything we've talked about has been linear. You're allowed to put quadratics, too. Let's jump up to the full version. If I have x squared minus 2x, 3x minus 1 over x minus 2, 2x minus 3, x squared plus 3x minus 1 squared, x cubed minus 4 squared. So I'm jumping to something gross. Again, we look at it factor by factor. When I see this x minus 2, I get a term over x minus 2. The x minus 2 is not to a power. I don't have to expand that. This thing is also linear. If I really wanted to, I could factor the 2 out and get x minus 3 halves. Most of the time, it's not worth it to do that. Just leave it as 2x minus 3. Putting fractions here is usually more trouble than it is to factor the 2 out, but it shouldn't be a big deal to actually factor the 2 out. This is just another linear factor. It's going to be b over 2x minus 3. When I have a quadratic, the top of a quadratic is not a constant. When you have a quadratic on top, you're going to end up with possibly as bad as a linear function on. When you have a quadratic on bottom, you should put a linear on top. So it's going to be something x plus something. I'll call that cx plus d, because those are the next letters I'm on. Just like with linears, if it's raised to a power, you got to count your way up. So I also get the same thing over that quadratic squared. Right? And similar, when you have a cubic, now you need a quadratic on top. The top is always going to be one step smaller than the bottom. X cubed minus 4 times, what goes on top? I'm on the letter G. Gx squared plus hx plus, maybe it's bad form to use an I. Like people say don't use the letter I. I think it's okay if you make it a super capital I. Like the problem with I is don't let it look like 1. Also, don't let it look like the square root of negative 1 lowercase I. Make a big blocky capital I that doesn't look like either of those. And again, with that thing squared, because it was squared in the original, we're counting our way up to squared. Jx squared plus kx plus L. So that would be the form of the partial fraction decomposition of this guy. The homework and probably also the exam will have questions that are just state the form, that are big and gross like this one. This one, by the way, is probably way too hard to actually do yourself with pencil and paper, and I wouldn't ask you to do the entire decomposition here. This is just about setting up the form. And I really want you to understand this thing about, I guess one of the things we should have thought about is look at x squared plus 3x minus 1 and double check that it doesn't factor. Or at least, if it does factor, I want it to not have 2 or 3 halves as one of its roots. Same deal with x cubed minus 4. It does factor into something, an x minus cube root of 4, into something else. Many, many places in life, I wouldn't want to actually deal with doing a decomposition with a j over a x minus cube root 4. Gross. I don't want to think about a cube root of 4. I'd rather not factor that. And it's okay to not factor it as long as you're doing the correct thing, putting quadratic over cubic, and also as long as none of these cube root 4 wasn't a root of any of these other polynomials. This is what you need to keep an eye out for. Okay, that's the form of the decomposition. I haven't stated the rules out, but I hope I've given writing this explanation out in a paragraph is pretty bad. I wouldn't want to try and write that paragraph because it's just super gross. But hopefully I've given enough examples that you see the point is the polynomial on bottom can be as big as you want. If it's got a repeated power, you need to count up that till you reach that power. If this was a power of 3, we'd have one more fraction here with an x cubed minus 4 cubed on bottom and a quadratic on top. That's the form of the decomposition. What was that? Step 2. Once you have the form, once the form is written out, you need to clear the denominators, multiply both sides by whatever is necessary so there's not fractions. Make the polynomial on the right look like a polynomial? You need to equate matching coefficients and then you need to solve the resulting system of equations. Cool. Let's try this out. Let's decompose 2x minus 3 over x plus 1 squared x minus 2. What's the form going to be? This is a over x plus 1, b over x plus 1 squared, c over x minus 2. I just need to figure out what a, b, and c are will make that true. I guess step 0 was, is the top smaller than the bottom? The top is linear, the bottom, when I FOIL it out, will have an x cubed. Top is smaller than the bottom. Check. I need to double check that this thing is factored all the way. This is broken into linear, this is as factored as anything's gonna get. It's factored all the way, and I grouped my like factors together. Check. Now I've written the form, and it's time to actually find the form. I need to multiply both sides by enough. Let's copy this. I need to multiply both sides by that common denominator. And then see what the rest of that sentence is saying. Multiply the top and bottom by x plus 1 squared x minus 2. I mean, just multiply both sides by this. X plus 1 squared x minus 2. X plus 1 squared x minus 2. X plus 1 squared x minus 2. What am I left with? U and U cancel. U and U cancel. U cancel with one of these. I end up with the left-hand side, I'll just get 2x minus 3. The right-hand side, I get a, x plus 1, x minus 2, b, x minus 2, c, x plus 1 squared. I'm hoping to figure out numbers a, b, and c so that this thing equals this thing. The key thing is the thing on the left I can see is just a polynomial. The thing on the right I can see is a sum of products of polynomials. I need to make this look like just a regular polynomial. FOIL out x plus 1, x minus 2, you get x squared plus x minus 2x is minus x minus 2, b x minus 2, c x squared plus 2x plus 1. If I distribute the a and the b and the c in, what do I get? Here's a step that you usually don't write out. I'll write it out this time so you can understand what's going on when we do this in our heads later. I get ax squared minus ax minus 2a plus bx minus 2b plus cx squared plus 2cx plus c. And now this is a polynomial. I want to group the terms by their powers of x. How many x squareds do I have? I have an ax squared and a cx squared. That's a plus c x squared. How many x's do I have? I have negative ax, positive bx, positive 2cx. So that makes this many x's. Do I have a constant term? I have negative 2a, negative 2b, positive c. Negative 2a, negative 2b, plus c. And this polynomial is allegedly going to equal 2x minus 3. I don't know if this fact is obvious to you. Here is a fact. The only way two polynomials are equal is if their coefficients are equal. Like x cubed minus 4x minus 7 is not going to turn out to be the same function as 3x cubed plus 6x plus 8. How do I know? Because the coefficients aren't the same. You don't need to actually prove that these are different. For a polynomial to be the same as another polynomial, you must have the exact same coefficients. This fact is surprisingly tricky to prove. You've got all the tools now. Cal 1 basically does it. So the only way this polynomial is going to equal this polynomial is if the constant term has to equal the constant term. So negative 2a minus 2b plus c needs to equal negative 3. The x coefficient needs to equal the x coefficient. So negative a plus b plus 2c needs to equal 2, and the x squared coefficient needs to match the x squared coefficient. Hey, wait, there is no x squared coefficient? That's fine, that's a 0x squared. It's going to equal 0. What's our x squared coefficient? It's a plus c. You always end up with a linear system of equations. Hopefully you've seen these in some algebra or pre-cal class in your life, and you've talked about them. And they're hard, or, I mean, they're easy, but they can be time-consuming. You've talked about substitution. Like in the abstract, you can always pick one of the equations, solve it for one of the other letters, plug that solution into the other two lines, and now you have one less equation and one less variable. So I can turn this 3 equations, 3 variables into 2 equations, 2 variables, do another substitution, turn the 2 equations, 2 variables into 1 equation, 1 variable. Once you get it down to 1 equation, 1 variable, you solve it, you back substitute those answers in. You can do it by substitution. Probably after you saw substitution, you saw elimination as a slicker way of doing it with less writing. Do whatever you want, but you got to be able to solve this thing. Here, the 0 lines are my favorite. It's really nice when there's a 0 because I can just say a is negative c. Now I can get rid of all the a's. Now these two lines become a is negative c, so that's minus c plus b plus 2c. That's b plus 2c minus c is c equals 2. This negative 2a becomes positive 2c, so that third line is negative 2a, negative 2b plus c, and another 2c will be 3c equals negative 3. So we've turned 3 equations, 3 variables into 2 equations, 2 variables. Hey, I don't know how hard you hit this when you cover systems of equations in algebra, but in general, if you're hoping to get a unique solution, and we are expecting there to be only one way to split this up into separate fractions, there shouldn't be more than one solution, and we're hoping there is one solution. If you want that to be the case, you need to have the same number of equations as variables. So when you reach this point, the number of equations better equal the number of variables. Here we have 3 equations and 3 variables, which is what we better be getting. Like, once I wrote down 3 ABC letters, I knew I needed to end up with 3 equations, and I did. Now I've turned it into 2 equations, 2 variables to solve it. I could solve this for b and plug it into there, but we'll do the slick way. Let's double equation 1, 2b plus 2c equals 4. The equation 2 is negative 2b plus 3c equals negative 3. If I add those 2 equations together, the b's cancel. I get 5c equals 1. C is 1/5. I can plug that into here to find b, but very often it's easier to just do elimination again a different way. This time I'll multiply the top equation by negative 3. Negative 3b minus 3c equals negative 6, and negative 2b plus 3c equals negative 3. This time when I add them, the c's will cancel. I get negative 5b equals negative 9, so b is 9/5. And I was able to do that without actually doing fractions in the middle. A is negative c, so a is negative 1/5. If I've done this right, it should turn out that... I'm just going to copy this line where I have the answer written down. It should turn out that A is negative 1/5, B is 9/5, C is positive 1/5. We should have now split that first fraction up into these 3 smaller, simpler fractions. If the problem was to integrate this, which it often will be, these 3 things are all easy to integrate. Remember, this is x plus 1 to the negative 2. The power rule works on it. You can do the baby substitution x plus 1, but that's the kind of substitution you're allowed to just do in your head. Sometimes the integrals are gross, but these ones are all easy. Did we do this right? This can be a pain to check your answers. To check my answers completely, I would need to take a common denominator and add these fractions, and I don't want to do that. A simpler way to check your answers is to plug in a number. Allegedly, there's the same function. That means that if I plug a number into the left-hand side and I plug a number into the right-hand side, I should get the same thing. It's tempting to plug in 0 because it's easy to plug in 0, or plug in 1 because it's easy to plug in 1, but I can imagine there being a case where the kind of mistake I make, like 0 and 1 are kind of special numbers, and maybe the mistake I make will turn out to be the same at 0 and 1. I'd rather plug in a number that's not special like 0 and 1. My favorite is plugging in 10. I like 10 because I know the powers of 10. Like if there's an x squared, I know 10 squared and 10 cubed off the top of my head, and they're easy to add. In this case, I plug in 10. So the left-hand side, evaluated at x equals 10, gives me 20 minus 3 is 17. This is what I mean. It's easy to plug in 10 because it's easy to multiply by 10. So I get 17 divided by, what's the bottom of the fraction? 10 plus 1 is 11 squared times 10 minus 2 is 8. So when I plug 10 into the left, I get this, 0.0175. When I plug in the right-hand side at x equals 10, I get negative 1/5 over x plus 1 is 11, plus 9/5 over 11 squared, plus 1/5 over 10 minus 2 is 8. I get, crap, not the same thing. Oh no, this is... have I done this right? Alright, let's check and see where our mistake went wrong. Okay, heads up. If you're in an exam and you discover that you've made a mistake, just stop this problem and go on to the next one. There's a million little tiny steps where a little tiny mistake can happen that is not the point of your calculus exam. If you messed up multiplying the 2 by 2 to get a 4 here, but like, it feels good to know you got the exact right answer. For the homework, try and get it all the way right. For the exam, like, seriously, there's so many horror stories of this problem being the thing that someone spent an hour on the exam. Don't stress too much over this. Prove that you know the method. I'm going to try and figure out what I've done wrong. If we did it, let's check and see if this ABC solution so like, I like the bisection theory. Instead of going from the very start, so somewhere between here and here, there was a mistake. Let's go to halfway. I'll go to here and see if our ABC values work here. At this line, a plus c, negative a fifth plus a fifth is 0x squared. That's what I was supposed to have, 0x squared. What's negative a plus b plus 2c? Negative a is a fifth, plus b is 9/5 plus 2c is 2/5. So it'll be 9. 10, 11, 12 fifths is supposed to be 2. That is not 2. There's what went wrong. So our mistake must have happened after this line. If we got the right thing here, that would mean our mistake was above this line. We got the wrong thing here. So our mistake is below this line. Something between here and here is wrong. Can I figure out what that is? A plus c is 0. That's right. Negative a plus b plus 2c is supposed to be 2, that's right. Negative 2a minus 2b plus c is supposed to be negative 3, that's right. What happens when a becomes negative c? This becomes positive. Oh, there's where my mistake is. Negative a becomes positive c. When I group that with the 2c, I'm supposed to have plus 3c here equals 2. Okay. So all of this stuff is wrong. Let's go back to this step. I'm going to copy this onto a new page. So this is plus a 3c here. Let's try and solve this the rest of the way. Let's double check that other step. Negative 2a becomes positive 2c, plus that c makes 3c. Okay. Cool. If I double row 2, or look at these two rows. If I double row 1 and add it to row 2, what does that turn into? This is a notation you use when you're messing with matrices. It's convenient to be able to do this without writing down the two rows you're adding up. Double this plus this. 2b plus negative 2b makes 0b. Double this plus this is 6c plus 3c is 9c. Double this plus this is 4 minus 3 is 1. I get 9c is 1. This time I'm getting c is 1/9. If I do... I can plug that in. I like redoing the elimination without substituting, because then I don't have to actually touch the fractions. I'm less likely to make a mistake that way. If I just take row 1 minus row 2, what does that yield? b minus negative 2b makes 3b. 3c minus 3c cancels, that's why I picked row 1 minus row 2. 2 minus negative 3 is 5. So b is 5/3. Okay. A is negative c is negative 1/9. This is what I'm getting this time. Let's check if this is actually a solution to this line at least. A plus c is 0. Check, that works out. Negative a, that's a 9th, plus b, that's 5/3, plus 2c, that's 2/9, is supposed to equal 2. A 9th plus the 2/9 will be 3/9 is a 1/3, plus the 5/3 will be 6/3 is, yes, that's 2. Negative 2a, that's 2/9, plus c is a 3/9 is a 1/3, minus 2b, a 1/3 minus 10/3 is negative 9/3, that's negative 3, that's supposed to be negative 3. Cool. Looks like all three of these equations are true about these three values. So let's see if we did it right this time. Our solution was supposed to be this. But now we know the a, b, and c. A we have found to be negative 1/9. B we have found to be 5/3. C we have found to be 1/9. If we did this right, then when I plug a number like 10 into both sides, I'll get the same thing. Let's see, when I plug 10 into the left-hand side, I get, same thing I got before, is 0.0175. When I plug 10 into the right-hand side, I get, what is negative 1/9 divided by 10 plus 1 is 11, plus 5/3 over 10 plus 1 is 11 squared is 121, plus 1/9 over 10 minus 2 is 8. I get 0.0175619835, 0.0175619835. Hooray! It looks like we got the right answer. Again, there's nothing special about the number 10. I think it would be a miracle if we did this wrong, but somehow when we plug in 10, we got the right answer. Yeah, we decomposed it. If I wanted to integrate the left-hand side, I would know how to do it because I know how to integrate the right-hand side. This is the method of partial fractions. I'm going to do one wrong now. Deliberately wrong to see what's going on. Let's actually do the integral this time of x minus 2 over x minus 1 squared, x squared minus 1. Hopefully you can already see what I'm doing wrong. If you don't, pause it and stare at that for a second. Do you see it? This thing factors. The fact that it factors isn't by itself the problem. The problem is that one of its factors is an x minus 1 needs to get grouped in with that x minus 1. Let's see what it looks like when this thing goes wrong. I'm hoping to decompose x minus 2 over x minus 1 squared, x squared minus 1. So, pretending I don't notice that problem I've built in, I'm going to get a over x minus 1, b over x minus 1 squared. This guy's a quadratic, so I need to put a linear on top, cx plus d on top here. Cool. Cool. To try to solve this, I need to cross multiply by the multiply both sides by the common denominator. X minus 1 squared, x squared minus 1. That clears with that. Both of these clear with that. One of these clears with this. I'm left with x minus 2 needs to equal a x minus 1 x squared minus 1 plus b x squared minus 1 plus cx plus d. X minus 1 squared is, oh gross, it's x squared minus 2x plus 1. Okay, I want to FOIL this part out. What is x minus 1 times x squared minus 1? It's x cubed minus x squared minus x plus 1, I believe, is what we get. This one, when I FOIL it out, is going to be 6 things. I don't really need to FOIL it out all the way. I'll just leave this one alone. I do want to split the c from the d. I'm going to write c times what? Times x times that stuff is x cubed minus 2x squared plus x. And then I get d times just the original. I like having a of this polynomial, b of this polynomial, c of this polynomial, d of this polynomial. We could distribute some more and then combine like terms, but this is a reasonable place to start writing down your answer. I'm going to have some x cubedses, some x squaredses, some x's. I'm going to get a constant term. How many x cubeds do I have? I get a x cubed. You have no x cubes. You're going to give me cx cubes. You have no x cubes. How many x squaredses? I'm underlining everything I do as I do it so that afterwards I can double check that every term from the last line got represented on this line. How many x squareds? I have negative a x squared from here. I have positive bx squared here. I have negative 2c x squared here. I have positive d x squared here. How many x's? I have negative a x here. I have positive c x here. I have negative 2d x here. I meant to switch colors, but I didn't. That's okay. Let's go to blue. What's my constant term? A minus b. No constant term plus d. I go through the last line. Did I use all the terms? I had 4, 5, 6, 7, 8, 9, 10, 11, 12. I've done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good deal. Hopefully we've done everything. Our system of equations becomes a plus c equals, how many x cubed are on the left-hand side? There are 0. My x squared coefficient is negative a plus b minus 2c plus d needs to equal the x squared coefficient. That is also 0. My x coefficient, negative a plus c minus 2d, needs to equal the x term is 1, and my constant term, a minus b plus d, needs to equal the constant term is negative 2. I got 4 equations, 4 variables. My number of equations should match my number of variables. It does. Good deal. So let's solve this. What do we get? The top one is easy to deal with. Negative a equals c slash a equals negative c. Let's get rid of all the a's. The other 3 lines now become, this negative a is a c. 1c and negative 2c makes negative c. I get b minus c plus d equals 0. I'll move the constants to the right-hand side this time because that's the normal way to put it. Negative a is c, so this is c plus c makes 2c. minus 2d equals 1. A is becoming negative c, so that third line becomes negative b. A is now negative c, plus d is negative 2. 4 equations, 4 variables has now turned into 3 equations, 3 variables. Do I want to get rid of one of these? I guess I do. Is there one I can solve for easily? I don't see anything. Oh, hey, look at the line 1 and line 3 have matching C and D parts, right? What happens if I take row 1 minus row 3? I get B minus negative B makes 2B. Negative C minus negative C is 0 C's. D minus D is 0 D's. 0 minus negative 2 makes positive 2. So 2B equals 2. So B equals 1. Cool. That makes this pretty easy to solve. What are my new equations I get? When I plug 1 into the top row, I get negative C plus D equals negative 1. Bottom row is not changing. 2C minus 2D equals 1. My last row, B is negative 1. Let's add 1 to both sides. I get that negative C plus D equals negative 1. Wait, what? Oh, these two rows became the same. Well, that's okay, because that's where they came from. So this says that C minus D is a half, and this line, if I multiply both sides by negative 1, tells me C minus D equals 1. Wait a minute, C minus D is going to have a hard time being both 1/2 and 1. There's no solution here. We arrive at a contradiction. The last one is impossible to solve because I end up with, like when I try to, if I solve the first one for C and then plug that into the second one, I'm going to get 1/2 equals 1. I can recognize it in this goofier form, but if I keep following whatever method I want to follow, I'm going to arrive at a contradiction. I get no solution. This is what happens as a result of our failing to accommodate the fact that this thing is not, one of these things should have been an x minus 1. So this is what it looks like when it doesn't work. If you get no solution, check and see if there are factors here that you should have factored some more. Or better, check first and then don't get the no solution grossness, because it's no fun. But this is what it looks like. Let's try and do this problem the right way this time. It was x minus 2 over x minus 1 squared x squared minus 1. We can FOIL this into an x minus 1 and an x plus 1. The correct way of writing this was as x minus 1 cubed x plus 1. This is going to break up into a over x minus 1, b over x minus 1 squared, c over x minus 1 cubed, d over x plus 1. A thing you can take a look at, if you think about this whole number of equations matching the number of variables thing, this thing on bottom, if I FOILed it out, I would have an x cubed here, and then x here will make it so that our biggest term when it's all FOILed out is an x to the 4. The bottom is a 4th degree polynomial. That tells me I should end up with 4 letters on top. Ending up with the same number of variables as in equations means that this number of letters on top is the number of variables. These to match the degree of the bottom will turn out to be the number of equations you get. So good. Signs are good so far. Let's clear denominators. X minus 2 equals. When I multiply the right-hand side, I need to multiply both sides by x minus 1 cubed x plus 1. And I want to do it without writing x minus 1 cubed x plus 1 over and over. What am I left with when I FOIL that out? I get a times x minus 1 squared x plus 1. b times, this time 2 of them cancel, I'm left with x minus 1 x plus 1. c times, this time 3 of them cancel, x plus 1. d times, this time the other thing cancels, x minus 1 cubed. I want to FOIL these polynomials out enough that I don't need to whatever. This one, it might be easier to do if I notice that this is x minus 1 times... Well, let's do the b one first. X minus 1 times x plus 1, this is a difference of squares. You get x squared minus 1. This one, because x minus 1 x plus 1 is a difference of squares, if I do those together first, it's not too bad to FOIL these two together now. So I'm left with a times x cubed minus x squared minus x plus 1. I get b times x squared minus 1. I get c times x plus 1 was ready to go. I get d times... Do you know how to cube a binomial in your head? It could be useful someday. It's x cubed minus 3x squared plus 3x minus 1. The 3's come from, you might have seen Pascal's triangle before. That 1, 3, 3, 1 is the third row of Pascal's triangle. They're binomial coefficients. It's good to see that at some point. Oh, you probably saw that in Cal 1 if you didn't see it here. Binomial coefficients. My research has me messing with binomial coefficients a lot. So I love goofing around with Pascal's triangle. And I want this to equal x minus 2. So I want x minus 2 to equal. How many x cubeds do I have? How many x squareds do I have? How many x's do I have? What's my constant term? My x cubes are, I have ax cubed. None, none, I have dx cubed. How many x squareds do I have? I have negative ax squared. I did red, let's do purple. Negative a x squared, positive b x squared. Come on. My stylus is cutting out. Oh, my thing crashed. Yeah, recover the note. You guys can't understand how happy I am my stylus is just working the whole time now. Ugh. Go back and watch those videos and listen for all the times I stopped talking for a second. You can hear me clicking the button on my stylus, trying to get it to reboot. How much did we lose? Not too bad. I want x minus 2 to equal. I'm going to have some x cubeds. I'm going to have some x squareds. I'm going to have some x's. I'm going to have a constant term. How many x cubes? A plus d. How many x squareds is? Negative a plus b minus 3d. What's my x term? Minus a plus c plus 3d. What's my constant term? A minus b plus c minus d. If you don't follow what I'm doing, I'm trying to avoid one line where we distribute the a into everything and then group the like terms and then factor them out. Like, I just want to be able to look at this and say, you are negative ax squared, and you are negative ax squared. So I have written them, I'm rewriting the same things, organized not by letter, but reorganizing by powers of x. And all the same terms are there. They were all the a's, b's, c's, d's. Now they are all the x cubes, x squareds, x's constants. Because that's how this is organized, and that's what I know about polynomials, is the coefficients have to line up. So I need a plus d to equal 0. I love those zeros. I need negative a plus b minus 3d to equal, what's my x squared coefficient? It is also 0. I need negative a plus c plus 3d to equal 1, and I need a minus b plus c minus d to equal negative 2. Can I solve this? This thing tells me that negative a equals d, or that a equals negative d. I'll use that to get rid of all the a's. Those three lines become these three lines. Negative a is another d. I get b minus 2d equals 0. Negative a becomes another d, so this is c plus 4d equals 1. I should probably be doing this step slower and more carefully, since this is the place I made a mistake last time. This is what I'm doing wrong. So like yesterday when I lectured and no one was watching, it went really badly, like laughably badly, like so badly that when I realized I wasn't streaming, it was like the punchline to the funniest joke. I told my wife the story of all the things went wrong, and then at the end it turned out I wasn't streaming, and it was just hilarious. I think the problem is I'm used to doing this in front of a room full of people. It is much safer to do math like this fast when there's a room full of people watching you for mistakes. Anyway, I gotta get rid of this a. A is negative d, so I end up with negative b plus c minus 2d equals negative 2 on the last line. This first row, the 0 makes this easy to deal with too. B equals 2d. I'll substitute that in. I only like doing substitution when there's a 0 because it makes it really easy to do the substitution. Once I run out of zeros, I'm going to be doing elimination the rest of the way. Replacing b with negative 2d, the first row became the rule that I'm using to rewrite the last two rows. My last two rows become, the first one stays the same, c plus 4d is 1, there's no b to substitute. This negative b becomes negative 2d, I get negative 2d, and another negative 2d makes negative 4d. c minus 4d equals still negative 2. This is easy to solve. If I add those two lines together right now, I get 2c equals negative 1. c is negative 1/2. If I subtract those two lines, row 1 minus row 2, I get no c's. 4d minus 4d is 8d, equals 1 minus negative 2 is 3, so d is 3/8. B is 2d, so b is 3/4. What's a? A is negative d. So a is negative 3/8. I've got a solution. I have a is negative 3/8, b is 3/4, c is 3/8, c is 1/2, d is 3/8. Let's try writing down our answer and see if it turns out right when I plug in 10. My denominator is x minus 1 cubed x plus 1. These a, b, c, d's I have constants for. A is supposed to be negative 3/8. B is supposed to be 3/4. C is supposed to be 1/2. D is supposed to be 3/8. Let's evaluate the left-hand side. Evaluated at x equals 10 gives me 8. 8 over 10 minus 1 is 9 cubed. I'm also dividing by 11. That's the left-hand side. That's a very small number. When I plug it into the right-hand side, I get negative 3/8 over 9 plus 3/4 over 9 squared plus 1/2 over 9 cubed plus 3/8 over 11. Oh, this feels terrible. Okay. Let's go back and see if these solutions are these actually solutions to this. Does a plus d equal 0? It does. Does negative a plus b, 3/8 plus 3/4 minus 3d. Oh, I can't even do this in my head. Let's write all these as 8s. This isn't 3/4, that's going to be 6/8. You're not going to be 1/2, you're going to be 4/8. Now maybe I can do this. Negative a plus b minus 3d. Negative a is 3/8, plus b is 9/8, minus 3d is minus 9/8. Yes, that's true. Does negative a, 3/8, plus c, 4/8, that makes 7/8 so far, plus 3d, 7/8, plus 9/8 is 16/8. Does that equal 2? No, it equals 1. Really? 3/8 plus 4/8 plus 9/8 is 16/8 is 2, not 1. Okay, so this line is not being true. That's what went wrong. Can I find where I made my mistake? Change a to a negative d in the second line. B minus 2d is 0. That seems right. So this seems correct. Negative a becomes a d. I get c plus 4d equals 1. That seems correct. Negative b plus c minus 2d equals negative 2. This seems correct. B is 2d. Change the b to a 2d, nothing changes. This seems correct. B is 2d. Negative 2d plus c minus 2d. That's c minus 4d. This seems correct. Add the two lines together, get 2c equals negative 1. This seems correct. That row minus that row, c minus c cancels. 4 minus 4d. 4d minus negative 4d is 8d, seems correct. 1 minus negative 2 is 3. That seems correct. So d should be 3/8. B is 2d, should be 3/4. A is negative d, should be negative 3/8. I can't see a mistake here. From here, leading to that solution, I went the whole way through it and didn't find a mistake. A is negative 3/8, B is 6/8, C is 4/8, D is 3/8, but row 1 is not true? Negative A plus C plus D is 3/8 and 4/8 and 9/8. It's giving me 2, not 1. Well, something's going wrong here in my solving a system of equations. I don't think you're going to learn much watching me trace over what went wrong. Hey, if you're watching live and you see what went wrong, text me right now. But otherwise, see if you can fix this and send me the correct solution. Anyway, afterwards we would have to integrate this thing. Each of these things is easy to integrate. This would be negative 3/8 natural log absolute value. Natural log absolute value x minus 1. This would be 3/4. The integral of something to the negative 2 is negative 1/2 something to the negative 1. It's the baby substitution that we don't have to do anything with. This one is 1/2. The integral of something to the negative 3 will be negative 1/3 something to the negative 2. Don't have to fix a constant because the coefficient here is 1. Plus this one will be 3/8 natural log absolute value x plus 1. This isn't the right answer because one of these numbers is wrong. Maybe all the numbers is wrong. I'm not sure what went wrong when finding the numbers. The mistake is not that interesting and is not something I'm going to take a ton of points off for if you make a mistake like this in the test. I guess giving up on this problem here means I'm not allowed to take any points off for the same mistake on the test. So that's the general thing about, that's the general method. Let me show you a couple more advanced tricks. Let's decompose 2x squared minus 8x minus 1 over x plus 2, x minus 3. When everything on bottom is linear, you get a really, really good trick that just lets you start writing down the numbers. When I was taught this class, it was called the cover-up trick, and I just freaking love it. Step 0, is the top smaller than the bottom? The top is quadratic, the bottom, if I FOIL it out, is also quadratic, the top is not smaller, we gotta do long division. Let's do the long division. I get x squared minus x minus 6. I need to divide 2x squared minus 8x plus 1 over x squared minus x minus 6. 2x squared divided by x squared is 2. Multiply 2x squared minus 2x minus 12 I learned subtract. You might have learned change the sign and add. Subtracting is adding the opposite. Do whichever one you're comfortable with. Don't try and mix and match. If you like doing it the other way, do it your way every time. Don't try it doing half and half. But for me, it's -8 minus -2 is -6x. 1 minus -12 is +13. So this function, 2x squared minus 8x minus 1 over, I want to use the factored version anytime I'm not doing long division, equals quotient plus remainder over denominator. This thing I know how to integrate, I just want to do partial fractions on this. Okay, time for the cover-up trick. Let's write the form of the decomposition. It's going to be a over x plus 2, b over x minus 3. And now here's how the cover-up trick works. I'm going to write down what we do. We do it in our heads. We can multiply both sides by one of the denominators. Let's do x plus 2 first. Then plug in the thing that makes that 0. When x plus 2 is 0, that's at x equals -2. I want to, in my head, multiply both sides by x plus 2, and then plug in x equals -2. And this is a thing you can do all in your head right now. I'm going to copy and paste to show off what I'm imagining. And also, by the way, this is all totally optional. What happens when I multiply both sides by x plus 2? This goes away, this goes away, this gets an x plus 2 on it. So it's called the cover-up trick, because I would put a finger on this thing, and I would put a finger on this thing, and I imagine putting an x plus 2 on there. What happens when I plug in x equals -2? When x is -2, this is 0. So now I cover all of this up. This is covered up, this is covered up. I cover up this x plus 2. What am I left with after I multiply both sides by x plus 2 and plug in x equals -2? The right-hand side is just a. Like, this is remarkable that I can just put my fingers over some things and imagine what's going on, and I can just write down a equals. What is a equals? It equals, what do I get when I plug -2 into the left-hand side, except cover up the x minus 2 part of the left-hand side? It equals -12 plus 13 over -2 minus 3. What is that? That is -1/5. A is -1/5. How do I get b? I want to multiply both sides by x minus 3, and then I want to plug in x equals 3. So I'm going to... Do I have a highlighter? I'm going to use a highlighter to show off what I'm covering up. Multiplying by x minus 3 covers this up. Multiplying by x minus 3 and plugging in 3 will cover all of that up. That's all gone. Multiplying by x by minus 3 clears that. So b equals the part that's left here if I plug in 3. -18 plus 13 is -5 on top. 3 plus 2 is 5 on bottom. I get -1. -1? Those don't usually simplify that much. That's the cover-up trick. Downsides. You know how when we made that mistake, we found the system was inconsistent, and we said, aha, we must have made a mistake. We're not going to discover that if we use the cover-up method. We're not figuring out that this A and B will make it always true. We're going from, if there are an A and B for which it is always true, then they must have these properties. So we're not discovering mistakes, but, so I wouldn't, you only really want to use this when the bottom is so fully factored that you couldn't make a mistake anyway. It's best when everything on bottom is linear with no powers or anything. Did we do this right? I would like to check one and actually get it right. I guess we did the first one right. Does this actually equal negative 1/5 over x plus 2 plus negative 1 over x minus 3? I got a feeling something's wrong here, because it's weird for one of these to be a fraction and the other one not to be a fraction. What do I get if I plug in x equals 10? I get negative 60 plus 13. I'm not going to try and do that in my head. I just suck at subtracting now. Divided by plugging in 10, I get 12, and also on bottom I have 7. That's the left-hand side. Plug in the right-hand side, the top is negative 0.2, divide that by 10 plus 2 is 12, plus negative 1, divided by 10 minus 3 is 7. Oh, they're so close, too. I got the same digits. Did I can't get anything right anymore. Is my sign wrong? A is 1 over negative 5. That feels right. B is, cover that up, plug in 3. I get a 5 on bottom. Negative 18 plus 13 is negative 5 on top. B is negative 1. Well, something's wrong. Oh, here's what's wrong. Negative 2 times negative 6 isn't negative 12, it's positive 12 plus 13. Makes this 25 over negative 5 is negative 5. I knew it was weird for one to be a fraction and not the other one. So the answer should have been negative 5 over x plus 2. So let's retype that in with, instead of a negative 0.2, if I make that a negative 5. Now I'm getting the right answer. Damn! I used to get these right every time. There's it split up using the cover-up method. If you're doing this right, I'm going to stop checking my answers because I don't think it's worth it. It feels good when they're right, and it just feels crushing when they're wrong. 2x minus 3 over, let's do x plus 1, x minus 4. Let's put an x here. Hey, heads up, when you see an x or an x squared or an x cubed, that means x minus 0. X counts as a linear thing. Seeing an x squared means you have a linear thing squared. That's going to contribute a 1 over x and a 1 over x squared, or an a over x and a b over x squared. It acts the same as those. It feels different to just see x squared by itself, but that's what it means. Here I'm making everything linear. This is going to be a over x, b over x, b over x minus 1, c over x minus 4. Let's see if I can write down what these numbers are using the cover-up method without doing all the writing out. Why don't you pause the video and see if you can just say what a and b and c are. I multiply by x and plug in 0. That gives me a. A is negative 3 over negative 1 times negative 4. It's 3/4. No, negative 3/4. How do I get b? I multiply by x minus 1, plug in 1. Cover that up, plug in 1. 2 minus 3 is negative 1. Over, plugging in 1 times 1 minus 4 is negative 3. I'm getting 1/3 1/3. That's a little bit weird. To get C, C I'm expecting to have a denominator of 12, given this 3 and this 4. I want to cover up the x minus 4 and plug in 4. 2 times 4 minus 3 is 8 minus 3 is 5 on top. Plug in 4 on bottom, covering up the x minus 4, I get 4 times 4 minus 1. Yeah, that's 4 times 3. It's 5/12. 2x minus 3 over x minus 1, x minus 4 should equal negative 3/4 over x, 1/3 over x minus 1, 5/12 over x minus 4. Let's plug in 10 and see if that's right. 20 minus 3 is 17. What do I have on bottom? I have 10 times 9 times 6. I know I just said I'm not going to plug it in anymore, but I feel like I need a win. 0.03. Plug 10 on the right hand side. Negative 3/4 over 10, that's negative 3 over 40. Plus 1/3 over 9. Plus 5/12 over 6. We did it. That's the cover-up method. Cover-up method works when you have linears with no powers. You can use it when you have other stuff, but it won't give you all the letters. Let's say I have 2x minus 3 over, let's make it x minus 1, x squared plus 1. Let's make it x squared. What's the form of this? X is repeated twice. I have something over x, I have something over x squared. I have x minus 1. I have a denominator of x squared plus 1. This one needs a linear on top, dx plus e. Hey, I wound up with 5 letters on bottom. If I FOILed out the bottom, it would be x squared, x squared would be an x to the 5th is the biggest power on bottom. That checks out. The degree of the bottom matches the number of letters on top. I think we're doing this right. How far can the cover-up method get us? If I multiply by x and plug in 0, I'll get something over 0 equals something plus something over 0. Like multiplying by x doesn't clear out all the x's because there's an x squared. So I can't get x from the cover-up method. To get the x, I would multiply by x squared and plug in 0. In the abstract, you could multiply by x squared, take a derivative, and that would give you an a equals, but you don't. It's not a thing you can do in your head anymore, so it's not really worth it. In the abstract, the cover-up method works if not just multiplying and plugging in, it's multiplying, taking derivatives, and plug in will give you the missing stuff that the cover-up method doesn't give you. We can get b and c though. If I multiply by x squared and then plug in x equals 0, then let's grab my highlighter. When I multiply by x squared, this will have an x, and after I plug in the 0, it goes away. This will have an x squared, plug in 0, it goes away. This will have an x squared, plug in 0, it'll go away. Multiply by x squared, I get b, there's nothing to plug 0 into. Multiply this by x squared, that goes away. Plug in 0, I end up with b on the right-hand side equals 2 times 0 minus 3 is negative 3 over negative 1 times 1. I need to end up with b is 3. Knowing that b is 3 can save me some work. I usually use it more like a check, depending on how gross the problem is. This one has 5 letters. I'm probably just going to say, well, b is 3, and I don't need to deal with that. If I multiply by x minus 1 and plug in x equals 1, what do I get? This will be c. Everything else becomes 0. All of that gets covered up. I'm plugging 1 into this. 2 times 1 minus 3. I get c on the right-hand side. On the left-hand side, I get negative 1 on top. Plug in 1. 1 times 2. I think c is negative 1/2. And I don't think I can get anything else from the cover-up method. I think in theory you can multiply by x squared plus 1 and then plug in I. I don't think that's worth it. You can try it. That doesn't It does sound kind of fun. Give that a try. I wouldn't rely on it on the test, though. I got these B and C values. Let's go ahead and just multiply everything out and see what we get. So this I'm going to put in my pocket and save for later when I get to the part where I'm solving the system of the equations. For now, I multiply both sides by the denominator. I get 2x minus 3 equals a times what? One of the x's cancels. I'm multiplying by x squared, x minus 1, x squared plus 1. I'm left with x minus 1, x squared plus 1. B is getting multiplied by what? The x squared cancels. I'm still multiplying by x minus 1, x squared plus 1. C, the x minus 1 cancels. I'm left with the x squared and the x squared plus 1. D, the x minus 1 cancels. Wait. Oh, that's the C. The dx plus e is getting multiplied by the x squared plus 1 cancels. I'm left with the x squared x minus 1. Okay. This is the worst one to FOIL out. If I multiply these together, I'm going to get x cubed minus x squared plus x minus 1. Multiply that by the extra x. I see it looks like it's a times x to the 4th minus x cubed plus x squared minus x. B times, what do I get when I FOIL this out? I just FOILed that out. I get this thing written here. X cubed minus x squared plus x minus 1. C times FOIL this out, I'll get x to the 4th plus x squared. I don't want to FOIL this out all the way. I just want to think about what is the D going to be. The D is going to have x times x squared times x minus 1. X times x squared will be x cubed x minus 1. That's going to be x to the 4th minus x cubed. E, what's the E got on it? The E is going to have just x squared times x minus 1. That's x cubed minus x squared. And this needs to equal 2x minus 3. 2x minus 3 needs to equal. Let's group together the x to the 4ths. How many x to the 4ths do I have? I have ax to the 4th. Hey, I tried to grab red. Ax to the 4th, cx to the 4th, dx to the 4th. So it's going to be a plus c plus d x to the 4th. I'm going to shrink that in because I'm not going to have a ton of space on this line. Cool. How many x cubeds am I going to have? I'm going to have negative a, positive b, negative d, positive e. X cubes is. I did that. 4 terms, yes. How many x squareds am I going to have? Ax squared, bx squared, cx squared, minus ex squared. How many x's am I going to have? I'm going to have negative ax. Okay, so I did the ax squared, I did the b. Oh, this is supposed to be a minus b. Minus bx squared. Okay. Plus c minus e. Okay. How many x's have I got? I have new color. Minus ax plus bx. No x, no x, no x. That's it. That's all the x's. Plus, what's my constant term? Oh, there's only one constant term. It's minus b. Huh. Oh, man. Is that going to... Oh. This whole b equals 3 comes out immediately because that's the only one with a constant term. That's not that valuable. That feels bad. So let's equate coefficients. X to the 4th. A plus c plus d equals 0. X cubed. Negative a plus b minus d plus e equals, what's my x cubed term? No x cubed term. What's my x squared term? I get a minus b plus c minus e needs to equal, x squared term is 0. What's my x term? Negative a plus b needs to equal 2. and negative b needs to equal 3. Are a and b the two that we got from the cover-up method? Oh, b we got from the cover-up method. A we did not. Okay, so we have a, b, and we secretly have c in our pocket. Okay, b is negative 3. Plug that into here. Negative a plus negative 3 equals 2. Add 3 to both sides. Negative a equals 5. A equals negative 5. I have a. That should be enough to... yeah, those first 3 equations now become a plus c plus d equals 0. I'm going to add 5 to both sides. Equation 1 becomes c plus d equals 5. Equation 2 becomes negative a is 5 plus b is 2. Move that to the other side as a negative 2. I get negative d plus e is negative 2. What's the third line? A minus b, negative 3, a is negative 5, minus negative 3 is negative 2. I'm going to add that to the other side and get a positive 2 on the right. I'm left with c minus e. Yeah? Yeah. Cool. I got 3 equations, 3 variables. A thing kind of often happens in these situations where, like, when you have 3 variables but they group themselves in pairs, it's sometimes worth thinking, what happens if I add all 3 equations together? If I add all 3 of these equations together, the e's will cancel, the d's will cancel, I'll be left with 2c. Hey, adding all 3 equations together gives me c immediately. 2c is 5, c is 5 halves. That doesn't sound good, because I got c was negative 1/2. Crud. Which of these went wrong? A is negative 5. C plus d is 5. Negative a plus b is 2. Negative d plus e is negative 2. Equation 3 became c minus e is a minus b is negative 2. So that should be positive 2. Add those 3 equations together. Get 2c is 5, c is 5 halves. I don't see a mistake so far here. Did I make a mistake in the cover-up method? That gave me c. Multiply by x minus 1. I should have c equals... cover that up, plug in 1. 2 minus 3 is negative 1. Over 1 times 2. That's negative 1/2. So I'm guessing the mistake had to be somewhere in here. Oh man, I don't... okay. I'm going to bail on this problem because I'm making mistakes too frequently. You find the A, you find the B, you find the C, you integrate all that stuff. It's gross. That's the idea of partial fractions, even if I'm not getting through as many completely correct problems as I would like to be getting through. I can do more of this on example day. Let's move on to our last topic for this exam, which is called improper integrals. Hey, is anybody watching me live? I have 1 viewer. I can never tell if that 1 viewer is me watching it right here in this little window. If you're watching live, give me a message, just so I know. I go a little bit crazy, not knowing if I'm talking to myself right now. It is a weird feeling. That's the idea of partial fractions. We're seeing it in the homework as integrals that become doable if you do the partial fractions thing. Yeah, so we did that, did that, did that. Where's my... yeah, let's talk about improper integrals. An improper integral is an integral is a definite integral, or it's an attempt to find the area of an unbounded region. For example, let's talk about the integral from 0 to 3 of 1 over the square root of x. What does 1 over root x look like? Root x looks like this. It's 0 at 0 and positive to the right, and it doesn't exist to the left. 1 over that will be decreasing, and when you try to divide by 0, it goes to infinity. So the thing I'm trying to do is find this area. That region is unbounded. If I try to plug 0 into this function, I get something like infinity. So you're tempted to say, this integral equals infinity. You can't do that, right? Well, maybe it is and maybe it isn't. There's this thing there's a principle in math. Sometimes you can add up infinitely many numbers and still get something finite. We're going to be headed there in a second. 1 plus 1/2 plus 1/4 plus 1/8. Or actually, we could do this even better. Here's a more straightforward one. What is 0.1 plus... Ooh, let's do this. 0.3 plus 0.03 plus 0.003 plus 0.0003 plus... Here's infinitely many things. When I add them up, I get 0.33333. In fact, if this is defined at all, it is defined to be the thing you get from adding those infinitely many numbers up. You can add up infinitely many positive numbers and still end up finite. The whole principle of decimal expansion is based around that rule. So maybe this part of the area is 0.3, and this part of the area is 0.03, and this part, maybe when I add those up, I don't get infinity. Maybe the total area in here is finite. Maybe it is infinite. How would I tell the difference? The key thing going on here is that if your integral, if a function goes to infinity, or plus or minus infinity, at a point, then the integral from a to b of that function is defined to be the limit as, I need to pick a letter that's not a. Let's call it the limit as, should I use alpha? Or let's say alpha goes to a of the integral from alpha to b. The integral at the place where it goes to infinity is undefined. But I can integrate from any number a little bit to the right of that and say, what happens if alpha approaches a from the right? So to figure out whether that area is finite or infinite, I say, what is this area at some value alpha, and then let alpha go to 0. I don't integrate at 0 right away. I integrate from something close to 0, and then let that closer get closer and closer, and see if, when you take that limit, is it finite or is it infinite? In this situation. And you can do the same hand thing for the right-hand side. So, if f of a is plus or minus infinity, which isn't technically the right way of saying this, but I think you understand what I mean. This is defined to be the limit as alpha goes to a from the right of the integral from alpha to b. And if you're undefined at b, if f at b goes crazy, this is defined to be the limit as let's let beta go to b, this time from the left. The limit from one side is weird. You haven't used that since Cal 1 probably, but when you imagine the picture, it's clear why. if b is the place where it goes crazy, and you don't want to actually integrate over the crazy part, you should integrate on a number that's always left of b. Don't let beta go a little bit to the right of b. You don't want to integrate from the other side of the undefinedness. You want to integrate from the safe side and let the safe side get close to dangerous. There are other versions. If f of c is the part that goes crazy, and if c is between a and b, so if you are trying to integrate your function over a place where it goes crazy in the middle, then it's defined to be, well, I'll integrate the left-hand side, and I'll integrate the right-hand side. This is a gamma, is a Greek c. And I need to let gamma approach c from the left, and I need to let here gamma approach c from the right. Here integrate f of x dx, plus here integrate f of x dx. So this is the integral of a little bit past gamma. Get that closer and closer to gamma. This is the integral from the left-hand side, right? I hope this makes sense. I have a place in the middle where the function goes crazy. If you want to try and integrate it from here to here, the way to define that is you say, well, I'll integrate from a to gamma, where gamma gets close to c. That'll give me all that stuff. Integrating from gamma to b. Now let that gamma go this way. It might be good to give them different letters. It doesn't matter. As long as the key thing is you have to compute the two separates separately. And this is only defined if both limits are finite. So this is if the function goes to infinity at a point. You can also ask to integrate a function out to infinity. Again, this is an unbounded thing, but if the things get smaller and smaller fast enough, and I want to define that, I might say, what's the integral from a to infinity of a function? This is defined to be the integral from a to, let's make it a capital B, and I need to take that as the limit as b goes to plus infinity. It's going to plus infinity from the left, but you don't have to say that. There's only one side you're allowed to go to plus infinity from. I hope these definitions make sense. This is a place where I would like to be looking at a room full of people and see on their faces whether they understand what I'm talking about. So, let's try that square root one. What's the integral from 0 to 3 of 1 over square root x dx? Well, this is defined to be the limit. I'm going to integrate from alpha to 3, and I'm going to let alpha get close to 0 from the right. I'll rewrite that function as x to the negative 1/2, because that's what I'm going to need to do to integrate it. What's the integral of x to the negative 1/2? It's x to the 1/2 divided by 1/2 is 2. Now I need to evaluate that from alpha to 3, and then I still need to take a limit as alpha goes to 0 from the right. So I get, what's the limit as alpha goes to 0 of 2 root 3 minus 2 root alpha? Does 2 root alpha have a limit at 0? You imagine the square root function in your head. Yes, it does. It's 2 root 3 minus 0. This works. It's pretty reasonable. When doing this function, to just ignore, not write out the limit, right? This will be x to the 2x to the 1/2 evaluated from 0 to 3. And the act of plugging in 3 should be the act of evaluating a limit. And if you did this, you would get the correct answer. But if you did this on the test, you would lose points, because on this upcoming first exam, I am testing you largely on your ability to write out the fact that this is a limit. Like, that is the key thing going on in this topic, is can you write this improper integral as a limit, and can you do that integral with that limit outside of it? If I had 1 over x, what's the integral from 0 to 3 of 1 over x? Well, 1 over x goes crazy at 0 also. So this is going to be the limit. Alpha goes to 0 from the right of the integral from alpha to 3, 1 over x dx. What's the integral of 1 over x? It's natural log absolute value of x. Evaluate that from alpha to 3. I ask what's the limit as alpha goes to 0 from the right of natural log 3 minus natural log alpha. I'm asking, hey, what does natural log do at 0? Having a picture of natural log x in your head is helpful here. As you try to take natural log of 0, you get negative infinity. I get natural log 3 minus negative infinity. That's natural log 3 plus infinity. We say that the integral equals infinity. This is a fancier way of saying that the limit doesn't exist. You're able to express a little bit extra information. It's not that the limit, not just that the limit doesn't exist, it's that the limit gets bigger and bigger without bound in a particular way. But I gotta contrast that with situations where sometimes I will get a plus infinity and the negative infinity. If there's a positive infinite part and a negative infinite part, I can't say that that equals infinity, and I can't say that that equals negative infinity. That thing's just undefined. This is the most dangerous version. There are so many places in calculus where you're going to be tempted to say, hey, what's the integral from negative 1 to 3 of 1 over x? Well, that's natural log absolute value x evaluated from negative 1 to 3. It's natural log absolute value 3 minus natural log absolute value negative 1. Absolute value of negative 1 is 1. Natural log of 1 is 0. This is ln 3. And this is wrong. And you can't tell what went wrong at all. Like, why is this wrong? What on earth is going on? The issue is that 1 over x goes infinite at x equals 0. And x equals 0 is in your interval. If you look at the definition of a definite integral, every fact they told you about when you're allowed to integrate things, it all had the hypothesis that your function has to be continuous on this interval from negative 1 to 3. And this function is not continuous. And it's not just discontinuous, it's like pathologically discontinuous. It goes to infinity. To do this properly, I need to split it up into the integral from negative 1 to 0, 1 over x dx, plus the integral from 0 to 3, 1 over x dx. Each of these will be a limit. This will be the limit as beta goes to 0 from the left, integral from negative 1 to beta, 1 over x dx. This will be the limit as alpha goes to 0 from the right of the integral from alpha to 3, 1 over x dx. I can do these limits. This is the limit as beta goes to 0 from the left of natural log absolute value beta minus natural log absolute value 1 is 0. Plus this will be the limit as alpha goes to 0 from the right of natural log x evaluated from 3 to alpha will be natural log 3 minus natural log alpha. This will be negative infinity. This will be positive infinity. Not only the integral doesn't exist, it doesn't exist in such a way that I can't even say it's infinity or it's negative infinity. There's a part of it that's positive infinity, there's a part of it that's negative infinity, and you're not allowed to add those. And this makes sense if I think about the picture. 1 over x is symmetrical, so this shape is the same as this shape, and the fact that this is infinite and the fact that this is infinite. Like, if they are the exact same shape, if I was allowed to cancel that positive infinite area and that negative infinite area, then that first wrong answer of natural log 3 we got would be correct. We're not allowed to cancel them. I have a plus infinity and a minus infinity that are just irresolvable. So that's an improper integral. You can also ask what's an integral at infinity or at negative infinity. I said the definition of that. Let's do one of those. Let's do the integral from 2 to infinity of e to the negative x dx. That's not a bad integral to do. I will tell you right now, it is really tempting to write this as, what's the integral of e to the negative x? It's negative e to the negative x. And I need to evaluate that from 2 to infinity. And when I write an infinity there, I can completely reasonably say in my head that I can't actually plug infinity into a function. When I say plugging infinity in, what I mean is taking a limit as something goes to negative infinity. And you can do that when you plug in infinity, e to the negative infinity. E to the x goes to 0 at negative infinity. So I get 0 minus negative e to the negative 2 is e to the negative 2, and put a box around that. That is a totally reasonable thing to write after this exam. This exam is mostly about, can you rewrite this as a limit? This is the limit as b goes to infinity of the integral from 2 to b. E to the negative x dx. This is the thing I have to grade you on, is can you write this down the correct way? This is a reasonable thing to do on paper as a computation. Plugging in infinity in particular is safe because you're always taking that as a limit. This square root example, where did I do that? If I hadn't written this as a limit, I would have been immediately taking 2 root 3 minus 2 times 0, and I would have gotten the correct thing. That feels like a safe thing to do, except that it's going to tempt you to do this wrong, where now when it's on the inside, you have to think about positive and negatives canceling each other. It's a slippery slope of what you're allowed to get away with not having to write out this limit. It's no fun rewriting your thing as a limit, but it's the point of this test. Do it right on this test, and then don't worry too much about rewriting it as a limit afterwards. I need the limit as b goes to infinity of this. What's that integral? The integral of e to the negative x is negative e to the negative x. Evaluate that from 2 to b. It's negative e to the negative b minus negative e to the negative 2. Take the limit as b goes to infinity. E to the negative infinity is 0. Yep. That's improper integrals. That's the last topic of the exam. That's probably the easiest of the topics on the exam. The main thing that we have left to do is, like we did integration by parts problems, and when I handed them to you, I said these are integration by parts problems. Use integration by parts to solve these. And then when we did trig substitution problems, I handed you some problems that said these are trig substitution problems. Use a trig substitution on these. The goal we have next is, if I hand you an integral, how do you recognize that this is an integral by parts problem and that one's a trig substitution problem? Trig substitution is a lot easier to recognize, like that when you see that form of thing, you try that thing out. But the thing we're going to be doing tomorrow and the next day, and I hope you can join me live and participate, is look at an integral, figure out what should we try doing on it. There are things that are hard, where I don't know what I should try. There are many tricky integrals. You'll see them in the homework. You now have everything you need to do to get through. Do I still have the homework list up? Here it is. You can get through 45. These are the improper integrals and whether they converge or not. After that is 46 through 60. No, 46 through 62 are the hard ones, where here's an integral, figure out what to do. And I'd encourage you to, I don't know what textbook you have, but there's a chapter on integration, and at the end of that chapter there's a bunch of mixed up integrals about figure out what to do on these. You should probably take a look at those problems. If not to do a whole bunch of problems, to at least look at and think about This one I know how to do, and that one I don't know how to do, so this one I should try a couple things on. Cool. Tomorrow I'm starting at 4. I hope you'll join me live. I'll see you then. End stream.